given role j is proportional to their current degree, the number of times I've seen them before, minus alpha. And the other term is if it's a new individual, I'm going to choose them with probability theta plus alpha times ni, which is the number of overall roles I've seen so far. And so the idea here is that we're going to be choosing in a way that's size biased. So if I've seen an individual, an actor who's been in a bunch of movies, Nicolas Cage, perhaps, he's going to be chosen with a higher probability than an actor who hasn't been seen often. And there's always implicitly a chance that an individual, a new actor will appear through this second mechanism. So the nice thing, so the reason the Hollywood model is nice is because you can say a lot of things about it theoretically. The first thing you can actually do is actually write down the probability distribution for this object. And so this is, any realization occurs with the following probability. You have the news pull out front, and then you have the second term, which we don't need to go through each piece, but the idea is you have different terms, and the overall thing matters is the number of isolated vertices, you have the number of vertices of degree k, you have the number of k-area edges, and you have total degrees, and this is the rising factorial term. Now, the reason I write this down is because it's not immediately obvious, but what is true is that if I look at this probability distribution, it's invariant to relabeling the order in which I see the movies. And so it is an edge exchangeable model in the sense that if I look at these movies and I thought about them in the order in which they appear, but I reorder them, and I say what's the probability of that realization, you're actually going to have the same probability. What can I also say about it from a theoretical perspective? Well, the first thing I can say is that the actual degree distribution, which is I look at each actor and I look at the number of roles they receive, that's their degree. And so I look at the number, if I look at the number of actors of degree k, and as n goes to infinity, that degree distribution is actually going to be parallel. Moreover, I'm able to say that what the expected number of vertices are, so this is the expected total number of actors in my data set, as n grows, is going to grow at this rate of n to the alpha. And so sparsity, the way we define sparsity in the paper, and I didn't want to get into it here, the sparsity depends on the size of the movie. So this mu term is the expected size of the movies, and so your sparsity is a function of, is alpha bigger than 1 over mu or not? So in the case of a binary edges, or let's say movies are only 2 people at every single time, then mu is 2, and so alpha bigger than a half, you're going to be dense, no, sparse, and alpha less than a half, you're going to be dense. My timer just disappeared, so. Okay. So this is a slide I put in because we had this little result on, oh! I'm sorry. Yes?
Sorry for all the questions.
Oh, no, it's good.
Okay, so the edge labels don't matter. Do the vertex labels matter? I'm confused because everything seems to be disappearing, and
yes.
That contradicts my intuition that something
So okay. So the so the way do the vertex labels matter?
That wasn't meant to be a joke, but I'm glad people thought it was funny.
No. The vertex labels matter in the following sense. If I label individuals in the order of appearance, the labeling actually is not arbitrary of the vertices because individuals who arrive early on are going to be seen more often and their degree is going to go up. And so we just had to choose a labeling of those individuals. We chose it to be in label of order of appearance. But when we talk about this edge-labeled, interaction-labeled object, we quotient out the labeling of the vertices.
Okay, so when you're looking at a probability distribution over some collection of objects,
yes,
you're looking at over the collection of objects where I've put an equivalence relation on any induced subgraph that has the same edges provided I do a wholesale permutation of the vertices. Is that right?
Yeah. So in the example I gave, I was labeling them 1, 2, 3, blah, 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 but I could have labeled them A, B, C, D, blah, 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 like weird symbols.
But however you permute the vertices, you have to retain the edges.
Yes,
so
and those labels are stayed the same. So that 1 through, so in that case, the 1 through 6 labels never change in all of these. and the only thing I'm at first quotienting out is the labels I've given to these guys. I keep the overall object the same, and the interaction labels the same. The vertex labels are getting removed.
Okay, so if I consider 1 existing because the pair 2, 4 shows up in my graph,
Yeah.
then I don't get to send 2 arbitrarily somewhere else, right? 2, 4, whatever those vertices were, they've got to get mapped to something that remains where they remain connected
You
by that
mean
end,
that
right?
the fact that I see 9 or 1, 2, 3, 4, 5, 6 things, that I have to keep them as labeled 1 through 6?
No, I'm saying, okay, so 2, 1 is the same, I could represent 1 also as the ordered pair 2, 4.
Yeah.
Right? So wherever I send 2 and 4, I have to retain that connection between
Yes,
them.
I have to. The labeling has to always be the same across all of them. So what 1 is really, so we're representing it as 2, 4, but it's the object 1, and the only thing that matters is that I need to know that 1 and 2, these 2 edges, share this guy as a matching one. That's the only thing I need to know to be able to link them up in that way. That's the only part of the vertex labeling that I'm using. That's the only reason I'm using the vertex labeling. But so 2 disappears, and then you're still left with the fact that I know 1 and 2 appeared this way. And then, for example, with 2 and 3, I now know, I need to know that 2 and 3 link up, but they're not the same as the way that 1 and 2 linked up. But the way in which, I could say that out loud to you that way, and not even use vertex labels to say that. And so, we're just using the vertex labeling to be able to link it up.
Invariant to a restricted class of permutations that preserves these relationships, right?
Yes, yeah.
Okay.
I'm losing the word, but yes, I'll think of the word halfway through and say it intermittently. Okay. All right, with 20 minutes I can get through what I need to. So the thing I wanted to point out here, because this is the karate example I gave initially. So what do people do? They do the thing that I had mentioned before. They turn it into a graph. Now, potentially fine, but what Harry and I found was that if you use these thresholding functions on interaction labeled objects, and I want to study the thresholded version of my interaction labeled object, what happens to the sparsity? Does the underlying does the underlying object change in some fundamental way? And what we show is that if you project, you go from something which could be dense or sparse to always a sparse object. So what we show is for binary Hollywood process with parameters alpha and theta, if we do any type of projection, so this one being one example, that, where we go, then the sequence is sparse almost surely for 0 less than alpha less than 1. So you are actually changing, by doing the thresholding operation, you are changing the sparsity of the underlying thing. So you're actually going to see that if you maintain the object, you could be sparse or dense, but if you do the thresholding, you're going to always be studying a sparse object. So this is just my little one slide impact of projection and thresholding in this case. So what I hear a lot of people do is they'll say, yeah, I have interaction data, but I can just say that there's an edge because, you know, 2 people were on the same piece of legislation, and I can throw away all of the, you know, how many times they shared in the on this, however many times. There's a legislation example that someone gave me once, and I was saying to them, no, the problem with that is that you're fundamentally changing the object from something that could be sparse or dense to something that is definitely sparse, and so you are throwing away information, but you're also changing the object you're going to study. And so this was what the slide is about.
Right, but you are working on the object that is a graph that has an edge if there's been at least one legislation that's been around.
Yes.
You are working on that object.
Yes. Which is, if that's what you want to work on, that's a fine thing. But if you're trying to say that I'm working on both things and that doing this one's going to give me information about the other one, that's where it gets a little bit worrisome. So I'll end this part of the talk with before I have my 10 minutes to do the new stuff, on the representation theorem. So so basically, under assuming an interaction labeled network, and that there's a consistency and the exchangeability assumptions, you're able to prove a representation theorem about those objects, which is here. The thing I wanted to mention, the only thing that I think for intuiting what is going on is important from the representation theorem, is that I sample f from some distribution phi, and given f, the way that this thing works is that I sample according to the probability that this k part of the object is equal to s is fs. And the whole point here, and the reason I bring it up, is this shows that vertices in these blip-free edge-exchangeable networks arrive in a size-biased order. If I knew f, the probability I see this, let's say in this case, person s is related to f sub s. So if f sub s is large, I'm likely to see them very early on. If f sub s is small, it will take a lot of interactions to see them. And so interaction-labeled objects, while they're exchangeable with respect to the interactions, the vertices are arriving in size-biased order, which is why you get the sparsity and power law behavior that you want. Okay, so the main not complaint, but the main comments that I tend to get on this work is that it's very nice.
It's a complaint.
It's a complaint. I'll call it not a complaint, but yeah. It's that this is a nice theoretical exercise to understand that you can have statistical invariance properties, achieve empirical results that you want, but that the way in which we did it through the Hollywood is actually not really how real-world networks work. And the reason, so there's two reasons. One is because in reality what we've done, and this goes I think to your question, when I look at each individual has a weight associated with them. If I knew, and so when I look at an interaction of multiple individuals, I don't take into account that there's sort of interaction terms between them. I sample each one subsequently. So basically, if I have any type of interaction between actors, so two actors who appear in movies multiple times together because they're friends, this type of model is not going to be able to achieve any of that. It's purely about individuals arriving in size-biased order. We're not taking into account any higher order things.
So you're saying such a model where comic actors will often be seen in movies together, that can't be interaction exchangeable.
It can, it can be interaction exchangeable. It cannot be achieved by this particular model. And so, yeah, this is the so you can the statement and this next part that I'll just go through briefly shows you can incorporate additional complexity, but maintain this edge exchangeable, interaction exchangeable idea. And the reason it's important is just because we're trying to move towards more complicated network structures, but not break the foundational stuff that we worked on. So this is this idea of hierarchical exchangeable interaction processes. So,
Can I ask one more question?
of course, yeah.
So how important is it that you actually generate the requirement that it be an infinite edge exchangeable random graph?
So the countable part matters in terms of the number of interactions. So usually if you're thinking about vertex exchangeability, with the graphons you're thinking about an infinite set of vertices. Here, what you don't need though is an infinite population of actors or vertices. So it's a slightly different thing. So if you think that your population is going to be constant, I'm in a karate club, there's 35 people, that's my life, that's it. You can incorporate that. That's my life. Yeah, it's not true. But so the population will be finite of vertices. But I'm thinking of the interactions, the number of interactions as being infinite. So this is what we assume. And so in our model, the Hollywood model, we assume an infinite number of potential actors. But you can actually set it to a fixed number of actors and say like 40 or bigger or whatever, if you think that that's the case. Ability to differentiate with the data at hand between is it a finite population or an infinite population, we're not going to be able to do. But usually that assumption is more baked into, do you think that there's a finite population or an infinite population that you're dealing with in terms of the vertex?
So it then depends on in the case of your 35 people in the karate club,
Yeah.
if you're going to allow for infinitely many interactions,
Yes.
it depends on your then being able to distinguish interactions between pairs of the same people, right?
Yeah, so this model will allow you. This model will allow you to say, I see multiple interactions between the same pairs of people, the same two pairs. So I will see 2, 4 over and over again, with some frequency, and I'll be able to capture that in this model. The way the Hollywood model does it, though, is it doesn't think of 2, 4, the pair. It thinks of 2 and 4 and some propensity for pulling out 2 and some propensity for pulling out 4. It doesn't take into account that if 2 always interacts with 4, you're going to see that very, very often. Yeah.
What is blip free?
Blip free is this notion that basically sometimes you can have, it's a mathematical constraint, it doesn't really happen, but you can have these things where a blip occurs where it pops up into your model and then disappears forever. So it's an actor who appears and then just doesn't reappear. And it's sort of an edge case that mathematically you have to deal with, but statistically I don't think that'll ever happen.
So
Yeah.
a follow-up to Aventi's question. So if we relate this generative process to the data process, for example, like clustering case. So we know the clustering case, you have the finite sample, right? So if you do the clustering, then the number of observed clusters is finite,
Yes.
but the number of latent components is infinite.
Yes.
So in that case, it's kind of like these components have it's empty component. So I'm thinking if the connection to here doesn't mean if you could only have finite number of samples but infinite number of edges. So does it mean like some edges potentially is like empty?
Yeah. So that you're exactly the intuition exactly right, which is that in the clustering case you might have you could assume in your model that you have a finite number of clusters and just do it that way, or you could assume an infinite number of clusters but you only see a finite number.
Right.
And so what we're doing in this model with alpha between 0 and 1 is you're assuming an infinite population of actors, but you've only seen a finite number of them, and the way that they interact is that way. Does that make sense?
Yeah, but it's different from what you just said about the edges. You see that 2 actors, they might have like multiple.
And then multiple, yeah.
But in the clustering case, it's kind of like just empty component.
Yeah. Sorry, what I meant the similar was that the way the actors appear, not the edges. So the actors appear in this way where you might potentially not have seen the actor yet because your sample is small, but you hold out the chance that you'll see him in the future. I wasn't mentioning the edges. Okay, with my 9 minutes, I will briefly go over this extension and why I think it's important. The reason is that in most of these cases, like in phone calls or in emails, you have a sort of higher order, so you have a sender and then multiple receivers, you have a caller receiver. And so you kind of want to take into account that there is sort of a potential relationship between a given sender will send to certain receivers, not the way the Hollywood works where you have sort of IID picks from that distribution. And so what we have is that the Hollywood model ignores that information, and we want to incorporate it, but we want to do it in a way where we're partially pooling this information, because if we don't want to do it where for each sender you build a Hollywood model, or for each caller you're doing different ones. And so the last part of this talk is all about how to do that. If you're thinking in the movie case, the simplest one would be that you have genres of movies, and so the fact that you know that Jason Statham's most likely in an action movie, or if you say an action movie, you're likely not to choose is a famous non-action actress. I don't know, but that's the way to do it. And so it basically boils down to the following. If you're thinking of the representation theorem, the way it worked down before was you have this multiplicative structure of FC and FR. And the way I want to think about it now is actually FC and then FR given C. The way we do it in the email case, where now it's not just one receiver but multiple, is I actually assume a sort of a conditional independence. So this goes again to your point, which was that if I'm not taking into account further higher order terms, in the sense that if you always are sending emails to pairs of receivers, I'm not going to be able to capture that. But what I'm capturing here is that for a given sender, I have potential to have different distributions over the receivers that I send to. The way we do this is not that it's sort of related to a lot of the standard tricks that you might see. We extend our ideas to have an unobserved global degree, and this unobserved global degree shares information across the local distributions. And so the way it works is you have the same terms as before. So this is that degree minus alpha that you saw before. It's local to that sender. But then you also have a global set of information that you can borrow from. And so the idea here is that you start in the local, if you decide to leave it, you decide to leave it with, you leave the local with an escape probability. So that's this guy right there. Oh, there he is. And then once you escape the local, you borrow from the global in this sort of, again, in the same fashion as you did locally. Now, this is now going to get, with 5 minutes left, I won't be able to go over everything. You can extend it and make it more pretty. The main point here is you've done more in terms of modeling and partial pooling. So you now are having local senders and then a global set of information you're partial pooling over. The worry is that you're going to lose this interaction exchangeability. The fact of the matter is you don't. So the point here is that you can incorporate a lot more flexibility in your models, but not lose this interaction exchangeability, which is very important for all those types of things we care about. Or it's very important from a statistical invariance principles perspective. And so with my last 3 minutes, I'll briefly go over the idea of the, so what can you say theoretically about this model? Much more difficult because now you have local degree distributions and globals, and how you share that information is much more difficult. So if you simulate from it, you do see that the power law degree distributions still hold. I can prove for particular choices of local parameters that the global degree is still power law. I can prove that if you assume uniform sampling from a fixed set of senders, you have this particular growth rate in the number of receivers, which is a little weird. So before it was just alpha, now it's alpha star, which is alpha times the max over the locals. So you can start proving things about this. It just becomes much more difficult to make strong statements because for two reasons. One, it depends on how you choose the sender distribution, and it also depends on these local parameters, alphas, a lot more. So if anyone's interested in proving strong theoretical results on these distributions, I'd be more than happy to set you up for that. So this is just to show you the power law behavior as a function of the local alphas to give you a sense of what's going on. So I can prove the global power law does not depend on the locals for alpha s equals 1. And so that's why you see this is the global alpha, and it should be a constant line. It doesn't look like the local alphas affect you that much. But local alpha equals 0, I can prove certain things, but I'm not happy yet. And between 0 and 1, it's a whole lot of mess. But you can see that the global degree distribution does not depend on the locals that much. And with my last 2 minutes, I'll briefly discuss the Enron case. So the Enron data set is an email data set, so you have emails from a particular sender to multiple receivers. And so if you look at the degree distribution, it looks like such. But if you look at particular senders, you have a lot of variability. So I just picked out the top 6. So some of them look kind of power law and normal, and normal being power law of that type. And then you have oddballs of this type, which this person just uses email to send notes to themselves. So that's an issue that we have not dealt with, but I don't know how to deal with that.
You calling me an oddball?
I do it too, but they do it to an extent that is quite a lot. I don't know what they're doing with their email and sending it to themselves, but it's...
This must be the CFO.
It must be. And so we have a Gibbs sampling inferential framework to be able to sample from this. The reason we use Gibbs is just because it actually makes everything easy. This is everything you need to do to be able to do this. I know, Carrie, I'm sorry. I am using Bayesian inference. The posteriors are pretty tight over global parameters, so you see that this is very similar to what I see in Hollywood models, which is that the alphas are pretty tight and it's pretty certain about the power law degrees, but the thetas are actually quite diffuse. And so the one point in my last 2 minutes I wanted to make is Hollywood versus Enron. Do you actually add anything by doing this? So globally, you actually see very similar results, which is good because Hollywood is actually just trying to do a good job fitting the global distributions. But locally, but what we do see is if you look at the total variation distance of these two models, Enron's actually, the one model with the hierarchical structure actually does a ton better on the total variation distance. It makes sense. It's actually quite nice. And then for the locals, you actually do a pretty decent job of the partial pooling, except for my favorite person. I don't know what's happening. The last things I'll mention is I'll end with this slide. So you can do some posterior checks on your model. The issue right now, as I see it, is the posterior predictive checks that people do if you're familiar with like Andrew Gelman's work. It's hard to use them here. The main issue is like for power fit. This is not the true, we don't know the true power law. We just fit a power law using, I think, Newman's method. And you can see that they're all pretty close, but in reality it's still ways off. And it's because we specify a model, and so it's because the lower order components, this part right here, if you fit to the whole thing, you're going to get very different tail behavior because Newman's method does a cutoff and just fits the tail. But in terms of other summary statistics, we do a decent job. Like this is the number of vertices in the sample. You can see both Hollywood and Enron do a good job. The Hollywood model does a horrible job locally. If you look at any local distribution, these types of models that are only global don't do well. But if you look at the Enron data, the Enron model where we do the partial pooling, in my last minute I'll just briefly mention this slide. What this is trying to do is look at 95% predictive intervals for different summary statistics and see if we're doing a decent job. And so what you see is we don't do a good job. So this is the minimum data cutoff. So this is how much data is on each individual. If it's above 10 to the 1, we'll keep them in. And so you see for the beginning we don't do well, but if you look at this mid-range we do pretty well, and then at the very tail we don't do well. And so if you look just in here, I think these 95% predictive intervals actually cover, goes up to like 85, 86%. So it's doing a pretty good job on the locals. There's obviously, what I'm trying to use this for as well is to see who are the outliers. Is there good reasons to try and overfit to them? How to do more robust fitting? But that's the current focus. And then the long-term focus, as Carrie is well aware, is that now that we've sort of structurally fit these models to the email data and sort of respected the structure and the interaction exchangeability, obviously emails occur in time, and so we want to think about temporal extensions. And the nice thing about the model, where did you go? There you are. Is there's various ways to correct the degree distribution, the degrees in continuous time to downweight the past. And we're looking into those to understand if we can achieve temporal models that have this partial. So I'm going to end on that, and I'm around for a while, so if you want to talk, feel free. Oh, wait.
Are there any additional questions for Walter?
Yeah.
So you said temporal. Is it possible to have some kind of dynamical, to give some kind of dynamical structure to the model?
Yeah. So for the temporal extension that I've been debating is you could so if you think in discrete time, which I'm not going to look at you right now, Karen. I realize. There's a potential for if in each one if I focus on a particular moment, I should have a model of this form. And so the question is, how much information transfers over to that next time point? And so in the simplest way is you could have a potential for getting of this degree that's sort of latent as well, in the sense that the degree decays but in a latent way. So you know I saw 50, let's say this was 50, it could go down, but you don't know that decay factor. There are other ways that are more explicit to do it, but what you're going to do is decay the past distributions into the future at different rates. The issue I've had with we're playing around with different extensions is the more you make things latent, the more you're unable to model anything and the thing hits you in the face. And so there are explicit ways to do it where you explicitly discount the degree. So right here, every time I see this person in this interaction, this goes up by 1. So that's the way it works. And so you can instead say, okay, if I didn't see you at this time point, but at a previous time point, you're no longer up by 1, but up by some lower constant, and that decays over time. Yeah?
You said that you're sampling edges, but in some data sets, like the emo data sets or the new data sets, you're sampling like a set of edges. Does it in any way affect
Yeah, so that's why, so we used to call it edge exchangeability, we still call it edge exchangeability, but I call it interaction exchangeable, because with the multiplicity and stuff, we are able to we're able to prove a theorem and talk about that fits in the framework. The modeling that we're doing makes assumptions about how that structure occurs. So in the case of the Hollywood model, the number of emails is just a parameter, or sorry, the number of receivers of an email is just a parameter, so new k. But the way previously in the Hollywood model, what it would do is it would just pull people with some propensity, and there would be no sort of taking into account that people are in emails in the same type of way. The new work, it's taking into account that sender distributions are different, and so you have different local f sub r's. The higher order, where you're trying to take into account that individuals, let's say that two individuals always appear in the same email, that is much more difficult. The way I think about it is you're slowly adding higher order interactions, and we all know that with normal linear models, when you add interactions, the amount of data you need to be able to say anything about those higher order interactions, it grows very, very quickly, and so the same thing is here, which is the only way we're even able to say anything about the locals is because we're doing partial pooling. And so as you add more and more, you're going to run into walls. But the nice thing is, at least for the posterior checks we've done, just incorporating the sender distributions and the partial pooling gets a lot of that done for us.
Okay, so Walter will be here, presumably in the next room for a while, but let's thank him again. What'd you think, Anton? Beach working. Thanks. Beach working. This beach working. The other option is big coal miner. That's not more fun. Working. It's better than working. Yeah, be better.
Yeah.
Russian. But he's not humorless. He's not.
So the computational, so the reason we chose that